How's everybody today? Today what we're going to take a look at is 1.2, finding limits graphically and numerically. Now this is going to be found on page 52 in your book. A couple of things you should learn. Estimate a limit using numerical or graphical approach. Learn different ways that a limit can fail to exist. Study and use formal definition of limits. Now here's the definition of a limit. If f of x becomes arbitrarily close to L as x becomes sufficiently close to A from either side, then the limit of f of x as x approaches A is L. Now I'll get into what all that means here in just a minute. Now the intuitive idea of a limit. The limit is the expected value of the function. This is what you expect it to be as you approach a number from the left or right. It may not be the actual function though. Limit notation. The limit as x approaches c of f of x equals L is read as a limit of f of x as x approaches c is L. Now here we're going to take a look at some examples. The limit as x approaches a of f of x. So here's my limit, here's my function as x approaches a of f of x. As it approaches a of f of x, what that is going to equal is L. Right through here. Now the limit as x approaches b of f of x. Now as we take a look, as we're getting closer and closer to b from the left or to the right, we expect that value to be k. Now the limit as x approaches 0 of f of x. As we approach 0 of this function, left or right side, it's going to approach 0. Now the limit as x approaches c of f of x. Now here's c. Now when we take a look, as I approach c, it's getting closer and closer on either side to m. Now the limit as x approaches d of f of x. There's d of f of x. That is going to approach L again. As we take a look, all these values are your y values, and these are your these are your x values. Now examine the given limit graphically and numerically. Now what we're going to do is we're going to take first the numerical approach. As I put in the values of x, 1.8, 1.9, 1.99, and so on, what you're going to get is the following. This will be 3.8 because I'm going to put 1.8 into this x and this x and simplify. When I put in 1.9, what you get is 3.9. When I put in 3.99, or 1.99, you get 3.99. When I put in 1.999, this is going to equal 3.999. Now this is as I approach x, as x approaches 2 from the left. This is the left side. Now I'm going to go from the right side. 2.01. This is 4.001. When I put in 2.01, that equals 4.01. When I put in 2.1, that equals 4.1. And when I put in 2.2, that'll equal 4.2. Now, what happens here at 2? If I take a look and I factor that numerator, we know that if x equals 2, it doesn't exist. Take the denominator, set it equals 0, you get an asymptote. But what happens here is those two divide out, the numerator and denominator. So what that means is we have a point of discontinuity is what it's called. So what I'm going to do is I'm going to go ahead and graph this x plus 2 on my graph. Now x plus 2 is just going to simply go through right through here. Now as I get to 2, when x equals 2, what I'm going to do is put in a hole. I'm going to continue that graph on. The reason that hole is there is to let us know that that divided out and there's really an asymptote there. But because these divided out, this is an indication what that graph's going to look like. It's linear. But when x equals 2, I have a hole there, which is a point of discontinuity. Now here's another example. This time we're going to go ahead and factor this first. Now if I take this denominators and I set them equal to 0, what I get are asymptotes at x equals 1 and x equals -3. So I'm going to put an asymptote right here at -3. Now what I'm going to do is go ahead and put in these values of x as x approaches 1 from the left and as x approaches 1 from the right. As x approaches 1 from the left, that simplifies to 0.263. This will simplify to 0.256. 0.99 simplifies to 0.2506. And this is 0.25006. At 1, it doesn't exist. Because again, you're going to have an asymptote there, but because these divide out, what are we going to have there instead? That's right, we're going to have a circle or a hole. And that hole is going to be right about here. Now let's go ahead and finish our table. When I put in 1.01, I get 0.24938. When I put in 1.1, this is 0.244. And finally, 1.2 is 0.2381. Now what your graph looks like is this. We end up with a vertical asymptote right here at x equals 3, and there's really one right there at y equals 0, because the exponent in the numerator is 1 less than that of the denominator. Now, when does a limit not exist? Well, when you have different right and left hand behaviors. What this will look like is, or here's an example of that. Now the graph of this looks like the following. So I have different right and left hand behaviors. It doesn't exist. Another example when it doesn't exist is when we have unbounded behavior. Now this is going to occur, or here's an example of that. The limit as x approaches 0 of 1 over x squared. Now you know that it's undefined right there at 0, because you're going to divide 1 divided by 0 is undefined, but what your graph is going to look like is this. It's not bounded. Finally, when you have an oscillating behavior, limit as x approaches 0, sine of 1 over x. See how it's oscillating back and forth? Your graph's going to look something like that. So notice it's oscillating as you approach it. It's not approaching a specific number because it keeps going up and down, and the end behaviors go off into positive and negative infinity. Down here's what I think you should do for section 1.2, talking about limits. Well, let me know if you have any questions, and I'll talk to you soon.